activity. Sharma sir is extension program focused on development, promotion and adoption of economical and accurate tools and technology in the area of agriculture and water resources. With this, I like to invite Dr. Vivek Sharma sir to deliver his lecture. Dr. Vivek Sharma sir, please.
Thank you so much for the introduction. I really appreciate that. Everybody can hear me properly?
Yes, sir.
Okay. All right. So I'll talk today about some of the agriculture water management technologies. What are some research and extension opportunities from field to regional scale. I'm introduced already, so I'll not go through some of my background, but in this particular presentation, I'm going to talk about some of the challenges in agriculture water resource management, what we are facing today in this world. I'll go through some of the development in the irrigated agricultures. Then I'll talk about more on the precision agriculture irrigation technologies. I picked three different case studies from my previous work that I'll talk about, which is more relevant to this workshop. One, I'll talk about variable rate irrigation management. I'll talk about some of the sensor-based irrigation scheduling. And then I'll also give some examples of how we can use remote sensing tools in agriculture water management. So let me start with the challenges and opportunities in ag water management. Today we live in a world where we are facing a lot of water challenges. Many regions in the world, including US and India, are already experiencing water resource and irrigation challenges. In this map, you can see all the red color are the areas which have more than 50% of water stress levels. These are the regions where majority of the population, about 36% of the population lives. These are also the regions where about 40% of the world grain production happen, which account for about 22% of global GDP. You can see that a lot of resources in these areas, but because of the non-sustainable use of water, we have seen this water stress. If we can zoom into particular areas, for example, US, this is the map showing you the water supply sustainability index for 2050. All the red and dark red color are the areas where we will experience a lot of water shortage by 2050. And these are the same challenges that we are facing in the other part of the world, including India, where we have about 54% of the India right now is facing highly extreme or extremely high water stress conditions. And there are many reasons associated with that. One might be the population increase. We experience about 80 to 85 million people per year adding in our pool, right? And other would be the increasing competition of water resources between different sectors. If you go into the more refined or the local scale, we have another challenges related to the availability of the freshwater resources at particular time and particular place. Other challenges like water quality. For example, in Florida, we have a lot of issues in the water quality. If we look at the northern part of India, Punjab, we have seen some of the groundwater declination issues in that state. And apart from all these, major factor is the climate change or climate variability. We have seen a lot of variation in the precipitation patterns across the world, change in the cropping patterns because of the change in the climate patterns as well. Because of all these factors, there is a huge pressure on the water resources, and since about 70% of the total fresh water that we withdraw either from the groundwater or from the surface water is used for agriculture, most likely, we will see that the pressure is on the irrigated agriculture. So under these circumstances, what we need to do? That's a big question, right? Out of many solutions that we have researched so far, one of the solution is the how we can develop integrated and pest management water and irrigation automated technologies so that we can manage our water efficiently first, enhance agriculture productivity. The most important is, I believe, is to promote water sustainability under changing climate conditions. But at the same time, we need to protect our environment. So we have to manage our irrigation such a way, or irrigated agriculture such a way that has less impact on the downstream users, on the environment. But when we look at this irrigation automated technologies, there are different parts of that as well. One is development of precision irrigation technologies like sensor technologies. We will use different set of arrays of sensors, introduce best management practices. The other would be, there are a lot of other parameters like climate, soil, crop, all those impact water, right? So if we can link all those variables together, there is another solution. And all those data sets, climate, soil, crop database are available at many locations free of cost. So these data sets help us to understand, the priority areas, where water resources are declining, where water resources, where we can focus our research on water resources. But at the same time, we'll talk about the precision agriculture technologies we can implement at a field scale, but I think it's important to address the issues both on field as well as on the regional scales. So again, I will cover these aspects in my presentation today as well. Okay, so before I move to all the case studies that I want to show you, let me talk a little bit about the irrigation development. Historically there has been 3 irrigation revolutions. We generally called as the blue revolutions, and it happens across the world. The first one happened back in 1800s and 1900s with the irrigation expansion. When we diverted water from big rivers to small canals to sub canals to our field to irrigate the crop. That was a huge development at that time. The second revolution happened back in 1950s with the introduction of pumps and engines so that we can extract groundwater. I'm sorry, here's a typo. It's 1950 here rather than 9150. So you can see about close to 1974, there is a huge bump in this huge increase in the irrigated acres in US. This is the graph showing you the progression of the irrigated acres in United States. And one of the reasons is with the introduction of pumps and engines, we were able to extract groundwater. And this is the same time when we see a lot of irrigated acres converted from surface to center pivot irrigation system. So center pivot irrigation system, sprinkler system is one of the systems that I'll talk in the next couple of slides. We use here in the United States to irrigate our crops. The third revolution is 21st century. Today's, present time, where we have not only the sophisticated irrigation equipment or systems, but at the same time we have better communication solutions or networking solutions, so we can link, water with other databases as well. So if you look at the world agriculture, today we irrigate about 326 million hectare land every year. China is the #1 irrigated country in the world, followed by India. US ranked 3rd in the nation, in the world, where we irrigate about 26 million acres or million hectare every year. So I will concentrate on US, in terms of the irrigation development. If we split this 26 million hectare of land of irrigated acre within the US, this is the spatial distribution of these acres, where California and Nebraska are the 2 leading irrigated states in the United States. And most of these irrigated acres being irrigated by, 3 different irrigation systems. Surface irrigation, we all know, surface irrigation, that is a flood irrigation or gated pipe or siphon tubes, where we let the surface water run over the surface from one end of the field to the other end. The other is the sprinkler irrigation system. Specifically, the center pivot irrigation system. This is the picture that depicts the center pivot irrigation system, in which we have a pivot point at the center of the field, and then this arm, rotate around the whole field. And these are the different sprinklers that we attached on the on that lateral pipe. This is the center pivot irrigation system, quite prominent in the States. And the third is the micro irrigation system, in which we have drip irrigation system, subsurface drip irrigation, on-surface drip irrigation, small micro sprinklers as well. So if you look at the distribution of these three irrigation systems across the states, and this is the sprinkler irrigation system, in which Nebraska and Texas, are the two leading states, where Nebraska, almost about 7 million acres, they irrigate every year using the sprinkler irrigation. If we look at the surface irrigation, California and Arkansas are the two leading states in surface irrigation. One of the reasons why Arkansas is among the leading state in surface irrigation is because of the rice production. And for the rice production, we probably need surface irrigation, quite a bit. The other is the more precision irrigation type is the drip and micro irrigation, in which there are many states, specialty crop states, where we use Washington. Look at California, about 41 million hectare of land. They every year they used under drip irrigation. Texas, Florida being a specialty crop state, we use about 5.2 million acres every year, based on the by using the drip irrigation systems. Okay, so these are some of the distribution of irrigated land in United States. Now I'll talk about more on the precision irrigation technologies. But if you look at the definitions, if you look at little deep, the old definition of precision irrigation management, we refer as irrigation scheduling. We still called as irrigation scheduling, but that was the term, that was given back in 1970s. Okay, let's use climate data or crop data to schedule our, crops. The new definition of precision irrigation management also account another dimension, that is a spatial dimension of water. That is the applying the water based upon the site-specific needs of a given location in a field. So now the old definition has been changed to the one that is the accurate and the precise application of water to meet a specific requirement of the individual plant or individual unit. Management unit. So, for example, this particular figure, show you the 3 different soil or 4 different soil types within the field, right? Each soil type have different water holding capacity. So, when we talk about nowadays precision irrigation management, we can use our irrigation systems to apply water variably based upon the water holding capacity of these soil types. So spatial variability within the irrigated field, become an essential component of the precision irrigation management. And there are different components or elements of precision irrigation management. One is the in-field sensing. Obviously, if we have different variation in the field, we need some kind of sensors to depict that change. Most commonly used is the soil moisture sensors, or now we have about multispectral cameras that we can install in the field to to account for the variation. Drones, satellite imagery. We can use canopy temperature sensors to sense the plant canopy temperature or other plant performance, soil variability. And the second component of is the decision making. We can use the data from all these in-field sensing instruments to make models, algorithms, a networking solution, web interface, and followed by the expert opinion. And the last component is the field operation. When we use this data, from the field, using different models and algorithm, and apply that into the field where we have more on the control and automation part. Okay, so one particular example, or one, I can say the key example of precision irrigation management is the variable rate irrigation systems. We also call as a site-specific irrigation management of the VRI. So the VRI technology assumes that the irrigation requirement may vary spatially within a given field. So for example, this is a center pivot irrigation system, and each color in this field depict a different irrigation requirement. So for example, let's say yellow one may have irrigation requirement of 1 inch compared to the blue ones, which only have the irrigation requirement of like a ½ inch, right? So with the variable rate irrigation systems, we can apply water variably for each particular zone in this field, which is split into different zones. So it allows the controlled or varied application of water over a particular area, or as I say, this is a zone based upon the observed and measured conditions. And the measured conditions, we can sense it using the soil moisture sensors, canopy temperature sensors, or the remote sensing, or satellite or drone. And there are other parameters that we can also sense and use for the variable rate, but these are the 3 that are most commonly used. Okay, types of VRI systems. There are 2 types of VRI systems we generally used here in my research lab. One is the sector and speed control, in which we increase or decrease or slow down the speed of the center pivot irrigation system to achieve the desired depth. If my system is moving fast, then it's applying less amount of water compared when my system is moving slow. It's applying more amount of water, right? The second is the zone control, in which we divide the whole field in different zones, and then we irrigate based upon each individual zone differently. Okay, so when we talk about variable rate irrigation system, the foundation of this technology lies on development of the prescription maps. So the prescription map is a base map that we feed into the irrigation system. Based upon that, the system will apply water variably. And there are 2 types of prescription maps. One is the static prescription map. So static prescription map is basically, we observe a certain property like soil moisture or soil properties, historical yield, aerial image of a field, and we have at the beginning of the crop season, and then we use that variable map throughout the growing season. That's a static prescription map. But generally, our irrigation requirement change within the growing season. So even for a crop, let's say maize, right? Let's say corn. At the beginning of the corn growing season, you require less amount of water compared to when corn tassel, you require more amount of water, right? So the variation, within season variation is very important to account for. That allow us to use the dynamic prescription map, where we sense a certain property like soil moisture, canopy temperature, or NDVI, for example, throughout the growing season. And then we use those numbers to spatially apply the water within the growing season as well. So I'll give you an example. For example, here in this picture, you can see different soil moisture sensors. These are all soil moisture sensors connected directly to a PC or using a web platform, where we are monitoring all those records, and then all the feedback from these sensors going to the irrigation system, which is you can see in the back, and then it apply water variably throughout the growing season. This is one aspect of that. But the problem with this kind of approach is, there are a lot of sensors in the field, and it costs money, for all those sensors. So this may not be an affordable solution, because as a grower who have 130 acres under this pivot, he cannot install 20 different sensors within the field, right? So we need to provide some another solution. The other solution is use of remote sensing, either the satellite images or the drone images. For example, these are the variation of leaf area index, NDVI, and crop evapotranspiration for the same field that I just showed you from May 15 to September 4. About every 2 weeks we have an image, and we use those image as a base map for the variation to feed that into the variable irrigation system for the spatial variation map as well, a spatial variation of irrigation as well. These solutions are affordable, but at the same time require some technical expertise so that we can calculate NDVI, we can calculate LAI, or if crop evapotranspiration, which is the crop water use at a given time. Okay, so once we have the prescription map, once we have the variable map, either from the soil moisture sensors or either from the remote sensing techniques, what we do is we use this remote sensing map, we feed into the control panel or decision support system to develop the VRI map. So I showed you this map before as well. So we feed this map to the irrigation system, and then the irrigation system apply water variably. And these are the units that we generally install on the irrigation system that allow us to water variably. So these systems are rely on the control on and off control, depending upon the amount of water that we want to apply. So this picture actually give you an in action, the variable rate system in action. You can see based upon the inputs that we provided to the system, you can see one zone is off. So that particular area of the field is not receiving any water at that point. These two look similar, but actually there is a difference in the water. This is approximately full irrigation requirement, and this is 25% reduction in the irrigation requirement. And you can see this is pretty clear from this picture that the variable rate irrigation system working perfectly fine in these kind of scenarios. Okay, so I'll share some of the results from one of the study that I did from my previous appointment at University of Wyoming, where I was working as an irrigation specialist in the state. So Wyoming is a very dry, very arid environment area where most of the crop system are heavily rely on the irrigation. So the idea was to understand the difference in the variable rate and the fixed irrigation treatments, and to develop the best irrigation management system, right? So we conducted this study at the University of Wyoming Powell Research and Extension Center. The soil type was sourland loam. There was some variation based upon the map that we received from the government agencies that we called here as a web soil survey. But we saw, when we were in the field, we saw there are changes. There are some, variability in the field as well. So what we did is we did soil sampling. That's pretty much basic for any kind of bees data. So we collected soil sample at different depths, and you can see we reach up to 3 feet of the soil profile. And these black dots here is the sampling locations, and you can see there is some variation in the percent clay, sand, and silt, right? And then we use these variables to further evaluate the soil water holding capacity, field capacity, and permanent wilting point of the soil profile. And based upon that, we saw there are 3 different zones, or 3 different zones that we can split the whole field. And then we have the plots in each of the zones. And you can see these are the plot locations, which is replicated thrice in each of the zones. And in each zone, we have 2 treatments. One is the variable irrigation using the soil moisture sensor data, and second is a fixed rate irrigation, based upon any kind of irrigation schedule that we can build. Okay, so we were using, I showed you this picture before, but we were using this soil moisture sensors. But overall result, you can see these graph is showing you the yield on the y-axis. Here is the irrigation amount that we applied, And here, yellow and green bars is the yellow bars representing the fixed rate irrigation, and the green bars representing the variable rate irrigation. You can see there's a significant savings, about 23% savings in the water that we have observed over the study period between the variable rate irrigation system and the fixed rate irrigation system. So these results showing there's a promising effect of variable rate irrigation, and again, the technology is a little bit expensive at this point, but there is a lot of potential. Many times you will see not just the water saving, but the nutrient saving as well, because these instrument can also allow us to apply fertilizer, liquid fertilizer, variably within the field as well. All right. So this is the one case study. The second case study that I want to talk about is soil moisture sensor technology. You heard, from me, I'm going to talk a lot about soil moisture sensors. I love this technology. I believe this has a lot of potential. But let's look at the progression. How soil moisture sensor technology has been evolved. If you go back 1970s or 1990s, we use gravimetric methods, where we collect soil sample from the field, we bring it to the lab, and then we weigh the wet soil, we dry it in the oven, and we measure how much is the volumetric water content, right? Other techniques like tensiometer, again, you have to take the manual reading. You install the tensiometer in the field, then you have to go constantly into the field to record how much is the soil water tension, or the nutrient probe, which is again the old method. Then we move forward. We started using data loggers, that can record soil moisture, for a growing season for a month, and there are different type of soil moisture sensors available with different data loggers. Nowadays, we are using some advanced type of soil moisture sensors with the help of the Internet of Things, like IoTs, where they can transfer the data directly to your web platform, where you can see sitting in your office, looking at the trends in the soil moisture sensor soil moisture sensor at a given location in the field. That is pretty handy and convenient, right? And there's a lot of potential of that because you save a lot of time, but at the same time, all these technologies are on the expense of the cost, right? That you have a cost associated with that, with the technology. As I said, there are a lot of companies nowadays. These are some of the companies that I found, you can see, and all these companies have their sensors that are different in their principle, different installation procedures, different web platforms. So we need to enhance the knowledge of our growers, who are using those sensors in the field, right? How we can do that? So to address this question, back in 2018, we developed this network called Florida Agriculture Soil Moisture Sensor Network. The main objective of this network was to, we have the soil moisture sensors as a team here in the University of Florida. We can lend this soil moisture sensor to the interested farmers so that they can try, they can play with the sensor and maybe, that help them likely adopt this sensor that may lead to the irrigation water and nutrient saving. But how our system is developed, we have specialists like myself. We have extension agents in different counties, who work regularly with growers. So what we found that it's very important for us to train our extension people because they are the first-hand people who are directly working with producers. And once we realize that extension agents gain information on soil moisture sensors, it's very easy for producer or grower to install or feel confident about what they are doing. So the idea was to provide advanced technical training to extension agent in the installation, in the use of soil moisture technology, so that they feel comfortable to share knowledge and skill with the grower. At the same time, other objective is We want to see the adoption of water and nutrient best management practices and the continuous expansion of Florida agriculture soil moisture sensor network. So what's our model? So we ask agents, extension agents to join our network. Then extension agent recruit participating farmers. Then we as a specialist, extension agent, farmer discuss the scenario, discuss the data that we receive from soil moisture sensors, and that will help us to refine the irrigation management in the field, farmers field, so they can also gain knowledge about how we are using the data associated with any particular field. Then farmer use the technology to modify the irrigation management. And the last, we also focus on how much impact water saving that we encountered over from the whole duration, how we can improve water use efficiency and water quality. As I said, in Florida, we have water quality concerns as well. Okay, so we use a lot of different technologies from different manufacturers, that is on the shelf sensors. For example, this probe is like 3 feet long probe that we install in the ground. We call it a Centec drill and drop sensor. We use Matos web platform so that we can acquire the data live. There is a BMP logic sensor, same probe but different web platform. Aquaspy is another. I mean, these are some examples. We use a lot of other set of sensors also in our network. At the same time, we just not rely on sensors, because sensors have some costs associated with that, right? We have developed irrigation apps as well, phone apps which operate based upon the soil water balance as well as soil moisture monitoring. At the same time, it accounts for the weather data. At the end of the day, we can also look at the spatial location of the field, what's the variation of the soil moisture, how much is the evapotranspiration, how they are inputting the irrigations, what's their depletion. So all those parameters are included in the apps. Okay, so as I said, there are a lot of other things that we focus on. One-on-one training. As a specialist, we generally go into the field with our extension agents. We show them how we can install the sensors accurately, how we can look at the data. So over the years, we have conducted different field days, different workshops, different one-on-one training, so that we can educate our growers as well as extension educators on the use of soil moisture sensors. This is an example of one web platform. So we are directly live data. We are getting it on our computers, on our dashboards, and then we will brainstorm. We will have Zoom meetings. We'll have in-person meetings to look at this data. What it tells us, how we can refine our irrigation strategies based upon this data. So that is really helpful. That is a really cool part of this whole program. And we look at the data, we are producers, we are extension people, specialists, all sit together and refine the irrigation management practices. Okay, that's great. So how we are progressing, right? So in 2018, we started this networks, in Florida, in North Florida, with just 16 probes or 16 soil moisture sensors. By 2019, we saw there is an interest among growers in South Florida as well. And you can see, in 2021, we have spread all across the state as well, accounting for about 45,000 acres. That's significant, which lead us to about 617 million gallon of water savings in just 3 years. These numbers tells a story by itself. We are not stopping here. We are constantly working on increasing the adoption of the soil moisture sensors so that people or growers can refine their irrigation management practices. Again, I'm showing you the number in water savings, but I can tell you there are a lot of savings on the fertilizer. How much, because your water is directly tied to your fertilizer. So fertilizer saving, energy savings are another perks that we can get by using the soil moisture sensor. All right, Okay, so we have seen some of the benefits, of using advanced technologies, automation systems on a field scale, right? But can we address this benefits on the regional scale? But when we talk about regional scale water management, one particular uh, component that play a very important role is crop evapotranspiration. That is the combination of evaporation and transpiration fluxes. It's a very important component of the hydrological cycle. Okay, so why we are looking at ET? I mean, definitely it's an important component of hydrological cycle, but how it is related to agriculture? It's directly related to crop productivity, irrigation requirement, groundwater consumption. Um, especially the irrigation reservoirs, storage, conveyance system capacity, all depend upon evapotranspiration as well. In US, there are a lot of focus on water rights. Especially in the western part of the states. Initially I showed you a map of US with the water stress index. You can see a lot of red on the western part because it's dry. It's a desert, and there are a lot of water rights, and all those water rights, policies have been developed based upon the crop evapotranspiration or the consumptive water use. But again, when we look at the regional scale, what tools we can use, and one tool that stands out is the remote sensing based estimation of ET. Either we can use satellite based, aircraft based, or a drone based, a crop evapotranspiration measurement using different models like surface energy balance techniques that can provide us a viable mean to map regional crop evapotranspiration. So to understand this regional benefits, how we can use remote sensing tools in quantifying crop evapotranspiration, we did the study again in the headwater state of Wyoming. Headwater state because we see a lot of water going from this state to other states, and there's a lot of court loss decrease associated with or between the Wyoming and other states. So it's very critical. And irrigated agriculture, account from 80 to 85% of the total consumptive water use. So we focused our research in the northwestern part of Wyoming, in a small region. I mean, it looks small. It's a very big region actually. In that region, we have 9 irrigation districts, and under certain given year, depending upon the availability of water, those irrigation districts require information on how much is the crop water use for a particular crop in that particular, in a particular irrigation district. So we try to solve this puzzle, how much is the crop water use for a particular crop or a particular region or particular irrigation district in this whole basin. So the idea was to compare different surface energy balance models or algorithms using Landsat satellite imagery to estimate crop evapotranspiration and other energy balance fluxes. The second was to quantify map, to understand the spatial and temporal distribution of ET. And the last that's important, where the irrigation districts was interested, is to quantify the contribution of irrigation toward crop evapotranspiration for different vegetative surfaces in different irrigation districts within the study area. So we were focused on that. There were some additional objectives for that in that study as well, but I'll focus on these 3 for now. So for the different surface energy balance models, we use 4 different most commonly used surface energy balance models: metric, Siebel, SEBS, and SSEBI. So metric, which rely based upon the assumption of the linearity between surface temperature and the air and surface air temperature difference, in which we required anchor pixels, which is the hot and cold pixels. So we selected different different combinations of hot and cold pixel based upon NDVI, LAI, and albedo. We ran those anchor pixels for many times, to make sure that our ET numbers are correct. SSEBI, SSEBS, SEBS, it rely based upon the turbulent fluxes and the wind speed profile. And SSEBI is based upon the relationship between the surface temperature and albedo. And you can see there is a difference between these models, how those models operate. So we use all those models and okay, so remote sensing, we are getting information from remote sensing. Okay, how we know those measurements are accurate or not, right? So in my team, we had this Bowen ratio energy balance system, which quantify crop evapotranspiration at the field scale at a very high resolution. So generally we get evapotranspiration measurements for every minute as well. So in 2017 we have sugar beet. In 2018 we have dry bean. In 2019 we have barley. So you can see we have tested our remote sensing measurement for 3 different years for 3 different vegetative surfaces. That provides more accuracy to our models as well, because we are providing the variation itself, so that our ET numbers can look more diverse. So these are some of the results. All the models indicate they are effective in capturing the variation. There are some, as expected, there are some variation among models. For example, this is the metric, Siebel, SEBS, and SSEBI. And most of the variation that we saw is based upon the, what's the land cover type. For example, in SSEBI, I highlighted these points because these measurement or these satellite images we collected before the growing season, when there was no crop. It's just the bare soil, right? So SSEB model or SEBS model, overestimate ET when there was no crop cover, at the surface. We also looked at the monthly comparisons because for irrigation district, we don't need field scale, right? Or we need a big number, how we can look at the temporal distribution of the monthly ET as well. Again, all the models, they can effective in capturing the variation of ET, but there is some differences as expected. One thing that we saw, when we were analyzing this study area, we saw 83% of the total study area in our image is just natural vegetation. There is no crop there; it's just natural vegetation. So again, natural vegetation behave totally different compared to a crop. Which is, for example, in the month of July, which is a peak month, your natural vegetation may look totally dry, but at the same time, crop look very healthy because you were irrigating it. It's a peak growing season, right? So we want to see whether we can also see the difference in crop evapotranspiration among different vegetative surfaces as well. And you can see the 3 middle graphs here, center graphs, that is the middle, growing season, where, the red, these peaks at the beginning, are showing you the peak for the natural vegetation, and peak in the middle of the growing season, where higher ET numbers is showing you the peak associated with the crop, and our models, effectively captured, especially metric and at SEBS, SSEBI and Siebel did not capture that variation, from different vegetative surfaces. Okay, another parameter that we looked into, the spatial variation, that's important as a parameter. But again, there are different crops grown in this area. This green areas, it's spatial variation of evapotranspiration from metric, SSEBI, Siebel, and SEBS. But there are this green area associated with the different crops. So we looked at different crops. For example, this charts representing the crop seasonal or May month crop evapotranspiration seasonal crop evapotranspiration from 4 different models for alfalfa, sugar beet, dry bean, and natural vegetation. These information is very valuable for irrigation districts, who can then look at their seasonal distribution. Okay, in one particular irrigation district, maybe the seasonal crop water use is 600 millimeter, compared to the other one is 400, right? So based upon that, they can manage their water allocations as well. Okay, this is again We looked at the different, in this table, you can see this is different irrigation districts, right? We conducted this study for 2 years, and this is the average crop evapotranspiration. And at the end, we looked at, how much is the percent of irrigation contributing to crop evapotranspiration, and how much irrigation water that is allocated to a particular irrigation district going to the other irrigation districts, or that's a return flow. So these numbers help us, help the irrigation districts in allocating water at a regional scale. So you can see here I gave you three different examples, two on the local scale and one on the regional scale, where we are using advanced technologies in managing our water effectively. All right. So in conclusion, I'll say, water resource management is very critical to ensure the future demand of food supply, energy, and sustainable ecosystem under changing climate conditions. Out of many solutions, one particular solution is automated irrigation management technologies that not only help us managing just water, but enhance agriculture productivity, promote water sustainability under changing climate conditions, less environmental degradation, better management practices. Under those precision irrigation technologies that we just talked about, soil moisture sensor or either remote sensing, if they are not affordable, it's very hard for us to implement those. So affordable precision irrigation technologies is a key for regional implementation. And again, we need to address the issue both on regional and local scale. It's very important as well, because when we analyze when we look at the problems at the regional scale, we can develop the water resource management strategies at the local scale as well, when we identify the priority areas. So with that, I'll stop here, and I'll be happy to answer any questions or any comments. Thank you.
Sir, we will ask for the student. Now, if any doubt, they will ask questions, sir.
Sure.
Any question? Sir, one question from the student. These are very good models, and these are fit for your Florida location. Can we implement this model at the semi-arid tracts of Maharashtra, or we need some modifications?
Yes, I believe you're talking about the remote sensing models, right?
Yes, exactly, sir.
Oh, yes, definitely. The study that I just presented, it's not in Florida. It was in a very arid location in Wyoming.
Okay.
So I believe that was very comparable to the situations that we have in India or Maharashtra, and these models can be easily implemented there as well.
Yeah, definitely. So we need some input parameters at in situ observations, and we need the spatial data. So we can modify the same thing for our locations also.
Yes. There are some base data set, for example, daily climate data set or land use maps, digital elevation models.
Wait.
Can you hear me?
Yes, sir, please.
Okay, what I was saying is there are some base data set that generally need to run those models, such as climate data set, land use maps or the digital elevation models. Once we have that, it's easy to run those models at different locations as well.
I hope it was a very
Thank you, sir.
All right, thank you guys.
thank you very much, sir, and hope can you listen, sir?
Yes, I can. Yes.
Okay, so thank you very much, sir. You are very good, exhaustive lecture, and hope this kind of work we will continue in Maharashtra also. And if any assistance required, we will be in contact with you, sir. Thank you.
Sure, I'll happy to help.
Yes. Thank you, sir. Good night.
Thank you. Bye.
Bye.
Within 5 minutes, we will start our second session. Let's look forward to our today's second session on Let's look forward to our today's second session on modeling control of unmanned aerial vehicles by the speaker Dr. A.K. Dev sir, Indian Institute of Technology, Kharagpur. And reporter for this session is Professor D.V. Patil sir. Welcome you both of you, sir. Now I request Dr. K.K. Dakore sir, please welcome today's speaker A.K. Dev sir by offering a bouquet. Also, I request Dr. K.K. Dakore sir, please welcome reporter of this session, Professor D.V. Patil sir by offering bouquet. Before start this session, it's my privilege to introduce speaker of this session with you. Dr. A.K. Dev sir received BE Honours degree in Electrical Engineering from Kolkata University, M.Tech in Control Engineering and Instrumentation, PhD degree in Electrical Engineering from IIT Delhi. He is working as Associate Professor with Department of Electrical Engineering, IIT Kharagpur, India. He taught several UG, PG courses and instructed their associate labs, sessional and seminars. He is mentor to Kharagpur KRSSG group. He was coordinated different workshop at IIT Kharagpur. completed his project, completed his research project with General Motors USA and Department of Electronic Information Technology, Government of India. He is presently involved in research project with Ministry of Human Resource Development, Aeronautical Development Agency, Bangalore, India, Ministry of Railways, Government of India, and UK, India collaboration in smart grids and energy storage. Sir received a student travel award from IEE Neural Network Society for attending IEE World Congress on Computational Intelligence in 2002 and 2014. Also, he published several papers in international journal and international conference, one book chapter, and co-authored the book Industrial Instrumentation, Control and Automation. With this remark, I'll invite Dr. A.K. Dev sir to deliver his lecture. A request Dr. K.K. Rakore sir, please welcome Deputy of today's session, Dr. D. Patil.
So, IIT Kharagpur is located to the west of Kolkata. And some of you should come here because we have this MOU with NAHEP, and that gives us the opportunity for students to come to Kharagpur and also do the research work. Some of you may have visited. Professor Sinde knows the collaboration will happen. Maybe some workshop will happen in IIT Kharagpur. The participants will be there when the situation is normal. So now the students are coming back to the campus. Almost more than half of the students are there. So things are getting normal. So now it is possible to do even similar workshop there. And in good weather, obviously in some winter. So if you visit IIT Kharagpur, this IIT Kharagpur is connected to our country's historical movement, history of our country. If you visit IIT Kharagpur, these buildings are there. This is basically an old building which was used during the freedom struggle as the prison. It was known as the Hijli detention camp where the freedom fighters were imprisoned. In fact, 2 freedom fighters were executed there also. The memorial is built in that name. So if you visit IIT Kharagpur, you will see these structures, very old structures. And this is the present main building where it was built by Pandit Jawaharlal Nehru, inaugurated by our first Prime Minister. Now, IIT Kharagpur over the years from 1950 with just 224 students, 224 students and 42 teachers, it grew over the time. And right now it has more than 40 engineering departments and centers. And all sorts of engineering branches are there, including agriculture and other departments. There is a law school, management school, now a full-fledged medical college is coming up inside the campus to support biomedical research. That one. There is battery problem. Okay. So this is just in quick, some work I did, with car companies. Some work I did with thermal power plants, some work with the steel plants. Some work I have also done with the Ministry of Railways. Now, in all this work, it actually brings modeling, estimation, and diagnosis, anything that needs to be modeled. But today I will actually present the work we have done on unmanned aerial vehicles, which has got a lot of agricultural application, UAVs or drones. And we are actually build the drones that lots of agricultural application that also needs modeling, needs estimation, and I will show. And today I also have another work which is called virtual lab, where we have developed all the labs in software and made available to the students through the internet, which is free of cost. And it has actually helped in during the pandemic situation when all the institutes were closed. Universities were closed, how to do the classes. Universities were worried. The theory classes could be done in the online mode, but what about the practical classes? So this virtual lab became handy to the students and universities. And this is a national project going on for the last 10 years, more than 10 years, 12 years. Started from 2010, and we didn't know, we were developing it. I was involved in this project from the very beginning. But during this pandemic, it became so useful to the universities. And we could see the monitor the lab usages. It has actually grew 30 times. Whatever is in the normal time, it grew 30 times, this virtual lab, and even international universities are also using it because this lab is available free of cost. And government has actually found the utility of this situation because pandemic was not known. When the whole country was shut down and universities were shut down, everybody was worried about the academic curriculum. So this virtual lab became a lot of use. Now this project has been extended up to 2026. No government project runs for 16 years. This project has been extended up to 2026 because the government found the utility of this project. And even during the lockdown situation, some labs were developed so that the universities could use it. So this virtual lab project, last time when I came to Parvani, and I am also the outreach coordinator that is doing workshops of virtual labs. So whenever I go to a new place, I don't lose an opportunity to give a virtual lab workshop there. So last time when I came here before lockdown, I gave this workshop at Nanded, SGGS Institute. Now this time I will give this workshop at Aurangabad. I have come via Aurangabad, so I thought why not give this workshop here. This Aurangabad is also not new to me. This is actually my third visit to Aurangabad. So whenever Professor invited me, I thought that I should give a workshop there. I got tied up with the Aurangabad Institute, and maybe some professor is there today. So I will travel tonight and give the workshop there, and then depart from there. That is how I did the plan. So this virtual lab workshop, but though for agricultural labs, there may be very few virtual labs. I exactly don't know the picture. But for other engineering branches, a lot of virtual labs have been developed. I am involved with it, and I am the outreach coordinator of this project. And this is another project where I am involved with it called Robo Soccer, that is developing robots that can play soccer. So this mouse is not working. Now this is the thing that I will discuss, that is decentralized target tracking using swarm of aerial robots, another project of MHRT. So this is the experience I am having to develop quadcopters, and I will basically describe on the quadcopters and some recent work we did. So all of you may be knowing that quadcopter is basically an aerial vehicle having 4 rotors. There can be 6 rotors, and quadcopters. It has low speed flying, hovering, vertical takeoff and landing. It can be used in search and rescue mission, surveillance, imaging, operation in hazardous environment, where there is a dangerous situation. Instead of employing a human being inside a quadcopter, support in agriculture, delivery, drone is used for delivery, then navigation and mapping. And for the swarm operation, we need cooperative transformation, communication delays, and all these things are there in quadcopter. The assumptions are it is basically a rigid model, symmetrical structure. If it is 4 rotors, it is a symmetrical structure. All of you must have seen drones. Center of gravity, body fixed, frame origin. It has got rigid propellers, thrust and drag to square a propeller speed. So these are basically some of the modeling equations This is governed by the physics. I am not going to the details of this, the quadcopter designs. I have been student my MTech, and now PhD students are also working in this quadcopter development. We actually develop the quadcopter, build the quadcopter, and use it for whatever purpose we need. So it basically has this. Suppose we consider a quadcopter, 4 motors. It has 4 motors placed symmetrically, and it has got a 6 degrees of freedom divided by 12 states. I am not going to this mathematical modeling, but these are done by the MTech and PhD students. Now, these are some of the equations to derive the state equations with respect to the frames. So, a quadcopter has its own body frame, and then it moves in an earth frame. So, with respect to the body frame and earth frame, all these equations actually come. And ultimately, these are the state equations
अभी शेयर करें,
वीडियो को अलग से शेयर करके दिखाऊंगा।
नहीं सर, अभी ऑन कर देना, अभी ऑन कर देना सर।
अभी शेयर में
हाँ,
जब वीडियो आएगा तो उसको स्क्रीन पर शेयर करना
हाँ
पड़ेगा,
शेयर करना पड़ेगा।
फिर वो अलग से वो स्टॉप कर
शेयर स्क्रीन कर दी क्या सर? अभी शेयर स्क्रीन करेंगे तो
अगर वीडियो
ठीक है, वो अलग से
कंप्लीट नहीं तो आएगा,
वीडियो पीपीटी में इंटरप्रेटेड है।
इंटरप्रेट तो ऑटोमेटिक आएगा।
ठीक है, नहीं आएगा तो देखना,
नहीं आया तो नहीं
नहीं आएगा। हेलो, 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 नहीं जा रहा। हेलो, 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 नहीं, वो तो इसी में लगेगा। नहीं, वो नहीं So these are some of the state equations. I am not going to the details of these equations because we model the unmet variable weighing from these principles from the laws of physics, and then implement it. Once we implement, the students implement the simulation, they actually go for it in the hardware. So now while selecting the components, it basically requires what type of application of the part coupler, the approximate air time, level changes done in pre-kit hardware, by zone circulation, one receipt event, and all those things are there. We work with the level of development is we buy the components like the basic motors, frames. We select the components and the controllers and the unit, and then make the quadcopter. The basic design flowchart has to be limited. That is the basic mass of the quadcopter is in the frame, the propeller design, the power to be given to the propellers. So in air time, basically means it will decide the battery capacity. Again, if we cannot put bigger batteries, if we put larger batteries, it will increase the mass. The flight controller to control the quadcopter. modes of control. There has to be a ground control station because it has to control from the ground. Equipment to support the main application. Whatever is the application required, then you need corresponding equipment. So that way you can optimize the components. So it depends upon the type of application. If we just need to have a imagery of the field, then we just mount the camera and then we have a certain focus. But if we have to do certain load to be carried, it can be delivering some load at some location, or in case of agricultural application, it could be some spray to be carried and sprayed. So that will again decided with the mass. So the payload will decide that. Now this type of frames we purchase. These are basically the span dimensions, the number of arms. If it is a quadcopter, then 4 arms. We are right now building one hexacopter also, and the weight, the angle of separation between the arms, then the PCB, what will be the PCB, where the PCB will be placed, and so on. And the propellers of the motor, the total thrust of the propeller is given by the 4 propellers. When the motor is rotated at maximum speed, the full thrust is achieved. The student do all these calculations and ultimately come up with the design. So these are the different forces that are working on the vehicle, aerial vehicle. It could be a quadcopter, it could be a hexacopter. That is the weight works vertically down, provides the lift thrust. Then there are sidewise forces. And whenever there is a sideways force for forward motion, there will be a drag, and so on. Similarly, the propellers are of 2 types. Some propeller will be in the clockwise operation, some will be in the anti-clockwise operation. So the propeller structures will be different. The propeller profiles. Similarly, different types of motors are there. Whether we go for brass or brushless motors. We go for brushless motors because it is compatible with more number of series LiPo batteries. No brushes. If there are no brushes, means there is no friction, and no friction means lower maintenance and longer durability, and better speed and torque due to the absence of brushes. Since there are no brushes, no friction, so it leads to better speed and torque production, wider speed range, better heat dissipation. Whenever a motor is running, it generates heat. All of us run some motors. In your home, you operate a ceiling fan or a pedestal fan or any other application where there is a motor involved. Maybe in a washing machine, and you see that equipment gets heated. So the heat dissipation is required for better efficiency of the motor, the more cost effective for high speed to power operations. So ultimately, these all qualities basically leads to the design for brushless motors for the consideration. Ultimately, for the motor, there are the electronic speed controllers, which we directly buy. So we directly buy depending upon the choice of the motor, and then we integrate it in the lab. So this is the picture of a frame where the 4 motors are connected. At the 4 arms, so it is a quadcopter, 4 motors. And in the central part, there is the main controlling. Below is there will be the battery, and in the 4 arms there will be the 4 speed controllers for the motor. Again, battery management is again an issue because it is all operated by battery. The battery that is there in the quadcopter has multiple purposes. The basic purpose is to provide power to the motors. Then it has to provide power to the different sensors also. And so battery management and maintaining the voltage level. So once it is in the air, the entire management has to be there perfectly. If the battery goes down, that is basically the heart of the quadcopter, and that will basically decide the the duration of flight. And so based on the application, you have to choose the battery. But again, the batteries are heavy, and so since it is a heavy, it will lead to the payload. So, but again, that has to be there. So this is again the battery integration, as it shows these batteries are connected, and they are filled in the central part of the frame, and that is how we make a quadcopter. And from there again through the circuit, the power goes to the four arms, as well as to the sensors. That battery integration is a very major issue. Similarly, all these batteries need to be charged. So there is a requirement of battery charger also. Whatever type battery is chosen for some experimental purpose, some batteries at the ground should be ready, such that whenever this battery charge goes down, it comes down, you can fit a new battery so that you can carry on with your experiment. So these are basically the different power modules, how the power gets transmitted or the power gets distributed to the motors. The power circuit has to be very effectively designed so that there is adequate voltage to the motors, and so as to maintain the total flight duration. So with the proper flight controller, we also need flight controller. A pilot's control input should correspond exactly to the behavior of the craft. A command from the pilot, that means in this case it will be from the ground, but the multi-rotor to move forward is fed to the flight controller, which determines how to manipulate the motors. So quadcopter, 4 motors are there. So 4 motors have to be controlled in 4 ways, and that has to be done in synchronism. Okay, so the command control should be such that it is perfectly achieved. If there is some problem in one of the motors, it may make the vehicle unstable because it is a multi-rotor structure. Okay, so even if such unstable situation happens, how to the robust technique would be that how the other available motors can run the vehicle. Similarly, it works on the GPS setting. Okay, there is a GPS module mounted on the drones that receive signals from the satellite. So at least we need 4 satellite data to get accurate position of the receiver. Okay, so until and unless that satellite data is available, it cannot be flown. So these are some of the PCB overlay and internal circuitry of the quadcopter. Some pictures from the ground control station. There are different types of autopilots. We mostly use the PCX 4-way autopilot. It is a cross-platform and supports all major operating systems. It communicates with the drone via a 933 megahertz transceiver. So a lot of technology actually goes in, when building the hardware, mechanical part, there is electrical part, there is electronics, communication, there is a lot of software involved to build it, and but again, it is a good experience to the students and us. For us also, we are learning when we go about this developing this new type of vehicle. Now, these are some of the quadcopters that we have built. These smaller ones we are actually purchased. These are small, which is just like the size of a palm. Small quadcopters. But these larger ones, which is maybe having a diameter of 2.5 feet. These are actually built, and some of them are already built and flown. I will show some video where we have demonstrated this, and we actually participated in a national competition where there was a particular target to be achieved, a particular mission to be achieved, and we basically succeeded in that mission. I will show the results. So this basically shows the F450. F450 means it is the frame size. The frame has got different types of names. We have used the F450 design, F450 frames, and then this is how it looks from the top. Again, there is some mathematical equations for modeling. I am not going to the details of this. If anybody was interested in all these quadcopter equations are available in the literature or in the papers, and MTech students actually have done MTech. MTech students are actually doing projects throughout 1 year. They do the simulation first, and then, if possible, they do it in hardware. Local in the last 1 year, it got disturbed. But right now, there is one student who is actually developing the hardware also. So basically, software, hardware, both is doing in the part of the MTech project. So these equations I am not going to discuss much. So these are the different types of equations are there. Lot of trigonometrical functions, then the force equations, and ultimately using these models, we go for the state space modeling. Typically, it has 12 states, and then those are used to generate the control action. So these are some of the simulation results, the quadcopter dynamics, and a lot of controllers are there: position controller, attitude control, and so on. Ultimately, this controller decisions actually has to go to the ESC, that is the electronic speed controller, ultimately to drive the motors. So again, we do a real-time simulation, which is basically using some software called the ROS gazebo. ROS stands for Remote Operating System. ROS gazebo software, we do the it looks like you get a real feeling like they are flying. And robotics people actually use this software, and it can be integrated with MATLAB Simulink. So first, the simulation work can be integrated with the real-time simulation developed using the ROS gazebo software. Programming languages, Python, MATLAB, all gets integrated. So it is actually this integration itself is a huge task. It takes time to properly integrate them, and sometimes Linux and all these operating systems are required. So these are some of the results done as part of an MTech project. I am not going to the details of this. So basically, the control force is generated in the form of 4 control actions: U1, U2, U3, U4, and that is that controls the 4 motors. These are some of the results for the attitude controllers. The parameters were used to tune using the genetic algorithm box. Some of you may be know these algorithms, genetic algorithms. MATLAB based toolbox is available. Just some of tuning results and responses using PT controller, nonlinear PT controller, and so on. Even if you have been tuned using fuzzy logic controller, we have applied sliding remote control and feedback lineation controller. So these are some of the controller results, and ultimately the controller performances were compared among different other controllers. This we have also developed a 3D soft simulation video. Similarly, if we have a hexacopter, it provides more power to the aerial vehicle, because if you have 6 rotors, whenever there is a 6 rotor, if we have to go for a high payload type of application, we can deploy an hexacopter, more power. The different frame sizes are HF 800, and it gives more power to the aerial vehicle. But at the same time, it will need a larger battery also. The battery management has to be proper. I'm not going to the details of the hexacopter. Some hexacopter is being built, but I don't have the extra results here on the hexacopter. Now, what I will focus now before telling about the application, the use of quadcopters or aerial vehicles it offers capability to integrate. By if you develop a quadcopter rather than buying a quadcopter, the advantage is you can design it according to your requirement. If you buy a quadcopter, modifying it may become a problem. So we go by the actual development, and it also reduces the price. But it needs integrated hardware software interfacing. That is anyway good because a lot of learning goes into it. I am also learning. And these controller algorithms have been implemented in ROS, Gazebo, Python, different types of languages are required. The controllers can also be implemented in real time. If we use this, since we are using the PX4 controllers, that is basically a real-time controller. Or if we have requirement of higher payload, then we should opt for hexacopters or more rotors, 8 rotors and so on. Now, this is one application that we have recently achieved is intelligent boundary surveillance. Suppose there is a boundary, it could be the boundary of a particular institute, it could be the boundary of a country, okay, and the boundary has to be surveillance that there should not be any intruder coming from outside. So we provided a swarm of quadcopter based application that if we can do it by using aerial vehicles, like the way we deploy security guards to monitor the boundary. So it will be done by basically the UAVs. And if any intruder is detected, it will give a signal. So it basically involves different components, PX4, ROS, Gazebo simulation, Q learning. We have implemented an aspect of artificial intelligence, which is called Q learning, that is used for battery optimization. Because battery is the heart of the vehicle, and it has to be optimally used. So we have used Q learning technique, which is basically an AI technique. So one PhD student basically used it, and ultimately we have used image processing for intruder detection. If any intruder is coming, okay, instead of a security guard, if our quadcopter can do it, it can take the images and it can relay back to the ground control station that some intruder is there, then the person can go there and see who is coming, not subsequent action is taken. So we have made use of image processing. I will show the results at the end. So the objective is to the surveillance of a boundary using a swarm of UAVs communicating with the control station. So we don't employ human beings, some UAVs will fly and relay to the control station that about the any intruder coming. Q learning has been implemented to deal with battery use optimization and charging and discharging event decision. Well, since multiple quadcopters are flying, their battery will dry down. Okay, so if all vehicles come down to charge the battery, then you don't have anybody to monitor the boundary. So there is some AI-based technique is used that which quadcopter will actually go for charging the battery. And when some aerial vehicle is coming down for battery charging, others will do the task. Then this will fly, and then the other can come down for battery charge. Okay, so a Q learning technique, which is based on a, which is basically a branch of an AI-based technique has been used. Similarly, image processing techniques have been used to detect an intrusion near the boundary and proper communication and to establish using the ROS Gazebo software. So these are the things already told that we ROS Gazebo simulation of the UAV surveillance, boundary and Q learning and image processing nodes are implemented. Image processing and intrusion detection are explained. I will just explain this. So these are basically some of the softwares, how internally the software works. And we have developed using, though it is multiple aerial vehicles, we have demonstrated using 2 aerial vehicles, flying 2 of them. If more aerial vehicles, it will lead to more complexity in the design. So we have named it as UAV 0 and UAV 1. That is two UAVs, and this is basically the circuit for optimizing the battery management. But battery management is very important. Okay, so when you have multiple vehicles, overall, what will be the battery management? Who will come down to charge while the others will do the task? When the out of the swarm, one is coming down the charge, the other should be able to perform the work. In this work, it is the boundary surveillance. And once this charging is over, it will again fly, and then the other one will come down for charging. So these are some of the internal software structures, how they look like. It is basically called software called Mavros. It is a graph of PX4 Mavros battery simulator. Q learning is implemented in the Gazebo environment. So internally, this type of relation holds in between the different nodes inside the software. This is just a image of we took the example of a racing track that is available, and ultimately we implemented in Gazebo and to monitor. These are some of the screenshots of the racing track. We will actually show an exact real life scenario. So this is the battery simulator. For two UAVs, basically we have the two nodes, node 0 and node 1. So we just told we named the two UAVs as UAV 0 and UAV 1. Then there is a waypoint planner. Waypoint means, suppose once you have a boundary, the UAVs have to move around a certain path. Okay, so the path has to be planned. The work has to be distributed between the UAVs. Who is going to take care of which part of the path? So the waypoint planner is there. So there will be some part for the UAV 0, there is some part for the UAV 1, and that part will actually decide the controlling of the corresponding UAVs. Again, the flowchart that has been used in Q learning for optimal battery usage of unmanned aerial system 0. So for each of the aerial systems, they have their own Q learning technique. This is for the second aerial vehicle, the flowchart for battery management using Q learning. So these are the Q learning programs when both of them are integrated. Both for the UAV 0 and UAV 1, if they are integrated together and the Q learning is implemented. Now the objective is to maximize the surveillance time. Whenever you are doing the surveillance, the entire boundary should be covered. It should not happen that for some time, some part of the boundary is not monitored. If some part of the boundary is not monitored, then it may lead to the intruder or your enemy use that time. If they get some information, then they may come in at that time. So maximize the surveillance time and minimize the number of battery recharge and replacement. The batteries have to be recharged and replaced. So how to do it in the optimal number of ways? So some minimization of the battery recharge and replacement is required. There are some constraints that the voltages should be higher than certain percent. If the voltages come down, then the motors will not be driven, the sensors will not get the power, and ultimately the UAV will not operate. So these constraints have been used that for the 2 UAV system, at least one unmanned aerial system has battery voltage higher than 25%. None of the 2 UAVs has battery voltage lower than 10%. Battery discharge time is 1% per unit time. Battery recharge replacement time is 7 unit time. Flight time between the two 8.65 unit time. So the time to cover between the two 8.65 unit time. So with these assumptions, we have designed battery voltage is again considered in different levels. 0 means the low state of the battery, 1 is the medium state, 2 means high, and 3 means the battery is fully charged. So the voltage level has been given some is divided into 4 parts. If it is fully charged, it is designated 3. If it is high, slightly lower than full charge, it is 2. Medium is 1, and extremely low is basically 0. Similarly, the actions. That is the action. That is when the decision is to continue the surveillance. The action is decided is given the name 0. When vehicle 1 return to battery recharge or replacement, it is got the name 1. And vehicle 2 return to battery charge and replacement is got the name 2. Similarly, these are the Q values. I am not going to the details of this. The Q learning techniques, based on a certain states, it decides the action. So these are basically the states, and then the corresponding action. This Q learning technique has been implemented. Total number of Qs. So these are some of the plots. I'm not going to the plots. It will not be interesting to you about these plots. Some Q values. Different battery charging and cycle. Battery charging cycle. When V1 equal to V2 equal to 100%, both the batteries are 100% charged. Similarly, V1 equal to 100%, V2 equal to 40%, two batteries. V1, V2 both 40% charge, and so on. So this type of boundary we have chosen for surveillance. So whenever there is a boundary, there we have demarcated by using waypoints, and just a single line, one just boundary, one wall, can be considered where there is divided into different waypoints, and these are the two UAVs. So the task will be divided between the two UAVs. That one UAV will operate between two waypoints, and the other UAV will be operating between the other waypoints, so that the entire boundary is covered. Some job distribution has to be done. And now if one UAV comes down for charging, other UAV has to take care of all the waypoints. So these are the different flowcharts for deciding the waypoints. So at the starting, it needs, how will the waypoints be known? The waypoints will be known by the images. Some images will be there, and each image will be earmarked for a certain waypoint. Like whenever we go from one place to another, we remember the turns, and which turn we had to, which crossing we turned left, another crossing we turned right, and then ultimately we reach the destination. And then we have to come back. We have to remember all those points. Then only we can go from one destination to another, and then we can again come back, move between the destinations. So those destinations has to be remembered by using the images. Okay. So while doing the surveillance, each unmanned aerial system captures the image and compares with the stored image. Some stored images are there, and then once it is moving, it captures images and comparing between these two, and then it will decide, okay, I'm in this waypoint, and then take the decision. So a lot of image processing algorithms are required, because ultimately that is the technology. So these are some of the algorithms, the loops that are used. I'm not going to the details of this. Similarly, there are unauthorized activity. How will you know the unauthorized activity? You have already the captured images. Now, when you take a new image with some person coming, so when you compare them, there is some difference between the two images, from the existing image and the image with same image where a person is also present. So that difference will actually lead to the decision that there is an unauthorized person, unauthorized activity. So here these are some of the results. So we did this simulation in the virtual environment. In a normal case, in the boundary, suppose we took the top view of the boundary, then there is no unauthorized person. Okay. But suppose the same boundary, same image, you see the same image, but some unauthorized person is there. So this is basically the abnormal case. So if we compare with this image with the earlier image, then some sort of a difference is there because this person is there is a person here, there is another person. So this difference will be generated by using certain value, some metric. The magnitude generated, some value is generated, and that value will signify that earlier there was no value. M1 was equal to 0. If we compare between when the image and with itself, then this magnitude is 0. But this image again, when compared with the unauthorized person, it basically leads to some value. So this magnitude will signify that there is a person which is an abnormal case. Similarly, again, if there are more objects, it will lead to more values, and it will lead to this magnitude will signify that it is an abnormal case. Now, this object identification, it was done in the gazebo environment, the same type of results. The earlier results was using the VRML toolbox in MATLAB, virtual reality ML, I can't remember, ML is machine learning toolbox in MATLAB. But this same work was also done using the Ross gazebo environment. And so here it is, the magnitude is 0, and whenever there is an object, it will generate a certain value. So that will signify that there is an intruder. So this same work, first it was done using the MATLAB environment, then it is done in Ross gazebo, and it has been done in taking the exact image of some locality. This is actually done by the student when he was during the lockdown situation, he was at his home only. So I told him, why don't you do this work from your home? You can work from his home. So he took this student was somewhere in Andhra Pradesh. So from his home, he took the empty road, took the image from the balcony. And then, so this is a normal case. So now if some other person or some bike is there, so it is basically the abnormal case. So comparing between these two images, it gives that there is an intruder. Okay, so you will see that the same place. So these are the here again this. These are some of the results. Here it's the same image. See, now there is a person here with a bike. So comparing with these two images, it basically shows that there is an intruder. It can detect, it can spot this deep difference. The image processing algorithm can spot this difference, and that basically signifies there is an intruder. These are some of the results by comparing the difference of the magnitude. Similarly, another picture, and these are the normal case. And here again the same picture where there are two persons in a bike. So comparing these two images, it signifies that there is an object, there is an intruder. So basically the difference of these images have been used for intruder detection. So whenever an UAV is flying to monitor a boundary, normal situation, it will have the images will be captured in its memory, and whenever some other object will come, it will compare with that image, and it will be done in real time. I will show we have actually achieved that in real time also. So this is the result that I am going to show. The algorithm that we developed. So how much time I have? So the algorithm that we developed, we actually participated in a competition. The competition was organized by the IEEE Vehicular Technologies chapter of Bangalore, IEEE Bangalore section. So whenever as soon as I saw this competition being held, and they wanted that it has to be done using multiple UAVs. The competition was that some application has to be shown using multiple UAVs, that more than one UAV. One UAV we all fly, we buy from the market and fly. But they showed some work or some target to be achieved using multiple UAVs, and they restricted the competition that at least there has to be 2 UAVs. Then, so many teams participated, and so this was the problem statement given, a working solution for coordination between 2 unmanned aerial systems to accomplish a task. That is, 2 unmanned aerial systems will jointly do some work and demonstrate the use of UAS communication and coordination in a realistic operational flight environment. In the operational flight environment, it has to be shown. So we gave our problem. The problem that we demonstrated was, the students, whenever the students showed me this event, they were worried what to show. They were thinking, carrying some payload. Carrying some payload also can be shown, but carrying some payload will be more complicated. It will need more powerful, and suppose some payload taken and dropped somewhere. The application will be complicated. I told the students, then why not make a image processing based application, where you just images, so taking an image will not increase the mass of the aerial vehicle. It will just carry a camera. It will just carry a small camera, so there is fixed mass. But if you have to carry 5 kilos, say 10 kilos, then to handle that payload will become a challenge. But that is okay. That also can be a problem. But we decided to do a camera-based work. So, and the problem statement we gave was intelligent boundary surveillance using UAVs. So this was a competition that started in 2020. But at that time, this lockdown happened, and in the initial stage, we had to make a video submission, and in the first stage, we actually became second out of the 11 teams chosen throughout the country. Initially, there were 32 submissions, and they chose the first 11. And in that 11 teams, we became second. This was the team: Ranjit Kumar, Kamal Sandeep, and Satyabrat South, these students. So in the first stage, since they became second, all the teams were given a prize money of 32,000 to build the hardware. So we basically achieved this boundary surveillance using swarm of aerial vehicles, communicating with the control station and among the UAVs. Q-learning technique was used for battery management, because battery has to be managed for optimization and charging and recharging event decision. And image processing was used for detecting the intruder. All the intruder detection algorithms I discussed, so that was implemented in real time. I will show the videos. The images will be captured by the camera, carried by the UAV, and then it will compare with the normal situation and give a decision that there is an intruder. So this type of closed boundary we considered. It can be a closed boundary. It can, so once it is a closed boundary, it has to be first do the piecewise detection of the individual boundaries. And these are some of the simulation results on the VRML environment. So this is basically so once the first stage, then the second stage, last year when the situation became a little bit normal, they declared for the second stage, where the teams had to demonstrate the hardware in Bangalore. The event was held on 27th November at Bangalore. So I went along with my 2 students. So since they had to show it in Bangalore, I sent them one day in advance. They have to dismantle the quadcopters, put in the suitcase, took it to Bangalore. At that time, there was a lot of rain and disruption in the train also. And we decided to take it in train because there are electronic circuits, batteries and all. There will be a lot of security issue in the airport. So we took it in the train. And they disassembled them, took it there. Train was 5 hours delayed. We planned that so that in 24 hours they can do the assembly, reaching at 7 a.m. But train reached at 12 p.m. So they, in the whole day, they do the assembly. They did the assembly up to midnight, and they tested in midnight for the event next day in the morning. And next morning, I also arrived. And so this is the actually the snapshot at the venue of the competition. And they actually became the first in the event. This is the certificate. They won the national award. Our demonstration very was nicely appreciated. And I will show a video about of the demonstration. So this was an event organized by the IEEE Bangalore Technology Society of the IEEE Bangalore section. And this is a picture of all the teams together. These 3 teams were there in the final. Others could not come, so they could not ready the hardware. But this is the 3 teams. Our quadcopters is here, and in fact, our quadcopters were of the largest size, and our flight duration was also high. There for the other teams, some of them even we saw that they had basically used purchased quadcopters. And I'll just show the video. Going from the beginning, in the video. Image is captured by the both the images are also shown. So, thank you. Just one more slide. So, these are acknowledgement of the team members who are working. Ranjit, Kamal, Sandeep, they are part of this team. And there are other early students who worked earlier in this type of work. A lot of work can be done here, modeling them, developing the hardware, and then developing for some application. And, thank you.
Thank you, sir, for such a nice presentation. And topic is open for discussion and anyone want any to ask two questions can ask. Any question from student?
Hello, sir. Very nice. We are able to training our books for irrigation systems. And any kind of design of the speech roads are very complicated. Yeah, not easy. Very problem is there. There are different issues that
Hardware, software, firmware, simulation, real-time simulation, and then once you are agricultural application that spray, carrying a mass. Yeah, so then the simulation more complicated, the battery management and all. We are starting, I am one of the key students because of lockdown, she is basically getting student, but she is interested. So in the online mode, whatever design she has done, the component fitting and all, that's after only she is planning to come and just start the work. But it's complicated thing, but it is also giving product for the independent level.
If you have any question, you can also discuss afterward. IIT campus faculty members in the mode of training, in the mode of research experiment, mode of any kind of research OT consultant, and this is a related work is there for all of the PGM students, I was faculty. There will be a program only training for research program, and even some of the students can join there partially the scholar students when they get accommodation in the part of the research located in the campus, and all those things which are you are combining performing, which you have excellent remark, which will be see that using the competition and any activity, they will be cooperating you in this regard. Sir, very much thank you. I have one submission for, from this campus. Nowadays, as this drone policy has been released by Government of India, and everyone aspirant from the farming society, 10th pass onwards, because the eligibility for pilot licensing by DGC, those who are 10th pass onwards, they can avail the pilot's license. At the same time, for limited payload capacity, they have their licensing classification also. Students are interested to join for the training. Some students are interested to join for the designing. Some students are interested for the any kind of competition or anything that comes around. So you already your suggestion in this regard that you are interested. Second, we are developing the components of the roads. Particularly for camera fixing, we are developing fixtures in 3D printer. So different designs and fixtures that I like to invite you for. Will there be any opportunity to combine? We have some projects in this regard. And apart from this, we are also interested to go for a hybrid type of robot come drone design. So those things which are we interested. Thank you, sir. Thank you very much.
All of this is possible in the student to take up some small project.
Yes, sir.
What targets and time bound. Each of them can do. They have to do some project.
Yes.
And then achieve the result. What coming over here? This from so because the lab
Somebody want to come to IIT Kharagpur. And the techniques like new learning techniques or the battery of is very fruitful for the future.
Now I request Dr. Gopal Shinde sir, please offer bouquet and memento to the Dr. A.K. Thank you, sir. Now we move towards our second session, Sensor for Smart Farming. Speaker of this session is Dr. T.K. Bhattacharya, sir, Institute of Technology, Kharagpur, and reporter of this session is Dr. S.S. Kulari, sir. On behalf of organizer, I like to welcome Dr. T.K. Bhattacharya, sir, and I request Dr. Gopal Shinde, sir, please welcome reporter of this session, Dr. S.S. Kulari, sir.
A very warm welcome. A very warm welcome on behalf of National Agriculture Higher Education Project established in Vasantrao Naik Marathwada Agriculture University. Today I am here to introduce our great mentor from IIT campus, Dr. Tarun Kumar Bhattacharya sir, who is in the electronics department. I think that it did not require introduction of our Tantra Bhishmacharya, because sir is very much aware of in this campus, and we all faculty members are very much impressed, and it is like to remain with Bhattacharya sir for our mentorships in design and development of sensors. Developed a very beautiful lab even though sir is very much attached with the students, in the application sales in the campus, students are facilitated with a very grand resource of the computing facility, internet technology facility, electronics technology facility, and sir is day night involved with the students. Because of that, every student makes his own life career path in the digital technology direction. I feel, sir, your guidance to this campus will be blessed, and we will be very much happy because we were awaiting for you to be in our campus. We will take assurance from you that soon you will reach to this campus, and everyone from this campus is interested to listen you, and also to get the guidance from you by the PG and PhD students and even researcher faculty. We are very much today harsh, and we are excited to listen you, sir, on this occasion, and you will be delivering us sensors for smart farming, as the main objective of this project is touching to the heart section, that without smart sensing, smart farming, nothing can be facilitated for the youth farmers, as they are now in the demands of these applications. A very small to a very high level of technology for robotics, for drones, the sensors, and without sensors, these all digital technologies and none of, I mean, the business, and it is meaningless, I should say. And the backbone of this is established in the IIT Kharagpur campus. So, sir, I kindly request you for this today's session to present and bless us with your address and the great information from IIT Kharagpur campus. Thank you, sir. Sound. Sir, can you please unmute?
So, good afternoon to everyone. And I am really very much pleased to be addressing this gatherings of students and faculty members. Actually, I was thinking going to your place. Can you hear me?
Yes.
Yeah. So going to your place, but as you know, this is the March, and being the head of a department, so very difficult to leave the campus. So actually, I did not find the occasions to go there, and hope by near future I will be definitely visiting that place. And we have already have a nice interactions with Pavani and Dr. Shinda's group, and we are trying and we are doing something together. Some of the glimpses of that I will show you. And so let me just share my presentation, okay, and give you that a little bit of introduction to the subjects called digital farming. So I share my screen and can you see the screen? Can you see the screen or not?
Sir, it has to unshare,
It is not in share.
unshare and then reshare.
Okay, so I am sharing that and then clicking the screen, but it is not going. So let me just 1 minute. It's not coming. So I am sharing it. So let's just be here. Share screen. Share. Can you see the screen?
Yes, sir.
Yeah. So let me go to the slides. Okay. So actually, I like to stress upon the idea of smart farming or digital farming from the eyes of emerging electronics. And I am professionally an electronics engineer, and nearly 3 decades I have been involved with research and teaching in my department, electronics and communication engineering. And I am associated deeply with the microelectronics and the VLSI development in IIT Kharagpur in the Department of Electronics. So currently I am now heading the group or center. It's called Advanced Technology Development Center. The department is the umbrella of hosting interdisciplinary research, so that there is no boundary of any of your subjects, specializations, to pursue research in a particular domain. Suppose any agricultural engineer wants to work in electronics. So this center will give him the opportunity for doing PhD in an interdisciplinary field, like chemical, biotechnology, physics, chemistry, civil, mechanical, are actually students from there and the faculty from there are involved with this technology center. And advancement of technology is the key motivations of this department, to get the best of today's trends in the technology node. So in these optics, we are trying to see that how that digital farming, which is the most important and relevant topics today, because everybody wants precision farming. Everybody now very much aware of the environment and nature, and also more crop per drop. So those kind of awareness is already with the community across the world. So from the conventional way of farming, definitely that is the basis of our technology. How this electronics, especially the nanotechnology, digital electronics, can help you out with an objective to make the farming more smarter, more accurate, more precise, and efficient. So let me share first with what kind of technology is emerging kind of a technology in electronics. Electronics is a vast field. So I will mainly go into the sensors. What kind of sensors, upcoming sensors, are coming up in tomorrow's world? So let me come from my own lab. That all of you know that flexible electronics, that is wearable electronics. So even you are now thinking of having electronics in your shirt, in your trouser, for sensing various property. And the underlying objective of any sensor development is first of all, how to fabricate that sensor technology, which will be pretty simple, and the carbon footprint should be as less as possible, so that the temperature requirement is much low. And you can have those things having low cost, I would say cost effective but efficient and more functional. So those kind of sensors. Now, if you divide the sensor in various domain or classification, there are one kind of sensor which is called qualitative sensor, yes or no, good or bad. And another kind of sensor will give you semi-qualitative, semi-quantitative. Yeah, it is much more or much less, or something like a relative estimation. So this is semi-qualitative or semi-quantitative kind of sensors. And other one is quantitative kind of a sensor, where we need the exact value of the sensing materials for some operations, for some functions. And this is the sensors what we have developed on a simple plastic. The electronics on plastic. So plastic electronics or flexible electronics or large area electronics, the cost will be much less. And the production will not give you, not take enough energy. So carbon footprint is much less. And so if you look at that, we have printed the circuit over there, the complete sensors on a plastic, and we can actually cut. So there are thousands of such sensors, hundreds of such sensors. Per go we can develop, and then we can cut it and give you a sensors at a much lower cost. So batch fabrication, yield, cost reduction is one of the major concern for today's sensor technology. So now the sensor technology, what is electronics inside? First of all, nanotechnology opens up a new completely era. So how this nanotechnology will come into the picture and make the sensor more effective. So it is called nano-enabled sensors or microsensors. And I give you a couple of examples. All of you know about graphene or carbon nanotubes. So how the use of graphene, very simple way of sensor making, and to detect something. Suppose I want to detect ammonia. where I'm just choosing arbitrarily ammonia. It may be carbon dioxide, it may be carbon monoxide, it may be nitrous oxide, it may be anything else. In the gas phase, or there will be some sensors which want to detect in liquid phase. Okay, so that we can check whether the water that contains the heavy metals or not, whether there is arsenic or lead or mercury, etc. Because you know that with the industry and our civilizations, we are actually contaminating the whole nature. Being it in air, airborne particles, being in water, then waterborne contaminants. And if you look at the farming, definitely these two are highly linked. But the kind of water, kind of air, and the kind of soil. So all these are quite important for monitoring. We call it health monitoring. So we talk about health monitoring for human being. But I am in opinion that let us make soil health monitoring. That is very much important. Yes, tell me.
Presentation is hanged up, sir. Can you make it in presentation mode, sir?
Yeah, now it is coming, the next phase. Next slide.
No, sir.
Then what, I should stop share and then start sharing?
Yes, sir.
So now you are coming to the, so let's see how it is. It is not. Yeah, it is changing. The slide is changing. Slide is changing. Hello. Is the slide changing?
No, slide is.
Right. The slide is not changing.
Yeah, it's changed now.
Yeah. So next we go to the next slide. So I talk about that. What is the today's sensor? And as an examples, I am just talking about how to detect ammonia. Okay. So let me go to this device and then coming to the materials issue. So this is the very simplistic view of a sensor. Suppose this is the interconnects. So gold having those kind of comb-like structure, these are the fin, and another this structure which are interdigitized. So it is two combs are actually attached and there are two connections. Why you have done this kind of structure? Because I like to have more effective area. Am I clear now? So now I put the graphene, I functionalize this substrate with the graphene with some biofunctionalized materials. So you can find out that I will broadcast, then there are some process, and that process will introduce the functionalized graphene. And when you talk about graphene, it is a reduced graphene oxide. The graphene itself having a band gap 0, so it may not be able to sense what you want to make a sensors. But when it is reduced graphene oxides, then you can open the band gap, and you can think of it that graphene shape as a semiconductor, and on which you can functionalize some biomolecules to have the selectivity of your sensor. So this is a very simple approach of making today's sensor. So it's a planar technology. So I'm not going in a 3D kind of a thing. Simple by metal depositions, I make interdigitized pattern on plastic or on silicon or other substrates. Then I introduce that RGO functionalized with some kind of a biomaterials. And now I expose it with, say, ammonia. These are the ammonia molecules. So, ammonia is toxic and is not very harmful for the human being. So ammonia gets absorbed into this kind of surface we call active surface. Then what will happen? That ammonia molecule will actually, depending upon its bonding nature or the chemistry, it will either donate electron or it can extract electron from the network. So that means it can enrich the carrier concentration or it can deplete the carrier concentration. Both can happen. One is called reduction, another is called oxidation. And these ammonia molecules, when gets absorbed to this graphene sheet, functionalized with biomolecules, then it is not a chemical bonding. I like to avoid the chemical bonding. In spite of that, we want to have some kind of a mechanical bonding or van der Waals force. So I don't need any change in their band structure or chemical property of either ammonia or graphene. Let their property be the same and let them get absorbed, called physioabsorptions. And then we'll see at the interface of this graphene or reduced graphene oxide and ammonia gas molecules, physioabsorb, and how this is going to impart or impact the transport of the carriers in this interdigitized structure. So what will happen if we drive a constant voltage? Then because of the change in the carrier concentration, the resistivity will change. So accordingly, the current will change. Or if we drive it through, say, constant current source, then the voltage will change. So the change in voltage or current, because of the absorption of the incoming gas, is the measure. So we can actually find out its mechanism. That is a physioabsorption based mechanism in which either the electrons gets donated from the ammonia or extracted from the graphene sheet. So in this way, we'll find that there is a change in its conductivity and it will change by current and voltage. So I give you a simple example. Suppose this is y-axis is the response. So I am actually checking the current. And then we flow, say, 400 ppm of ammonia. Then we find suddenly the current picks up. So current picks up means it actually gives more electrons, more carriers and more current. And then I stopped the flow of ammonia and immediately it gets down to its base value. So you see that it is picking up while the ammonia is getting exposed to the system, this system. And then again it is going down when it is stopped. The flow of the gas is stopped. Again I starts with 200 ppm. Then it picks up at a lower value. And again it stops and we can on and off with the gradually decreasing ammonia concentration. So my current is reducing accordingly. So what I think, that it gives you some approach that if I can calibrate the current, the maximum current at a particular gas flow, and I can make some kind of a lookup table or using some sort of a heuristic search or some kind of a AI-based techniques, we can actually semi-qualitatively, we can do it immediately. That I can say that when peak is less, then I will say less ammonia, or if the peak is high, then the consecutively the peak is high. The ammonia is high in content. But one of the thing you should be able to understand that every time when ammonia gets out of the systems, then it immediately catches the background. So it is not that it is falling down to a mid level and again when it is exposed to the new gas, it again going back. So this residual phenomena is completely out of this kind of structures. All of you know that the sensor gas adsorptions or even liquid phase sensors, there are many in the market. So what is the big thing about it? What is the new, we call it emerging technology about it? The emerging technology is that I do not need any additional heater, so that when the gas gets absorbed to the sensor, then the residual phenomena or background phenomena would not occur when it will be exposed to new flux of ammonia. So it is always going back to its original phase, to the background. So you can see that. So that means that we are not having any residual effects. So we do not need any micro heater to heat it so that the residual gas gets deabsorbed and removed, and then the next phase of ammonia comes in. No, we do not require, because this technique, as I mentioned, is entirely on charge transfer, either to the system or system to the gas. So either the current will be more or current will be less, depending upon what kind of gas, whether it is oxidizing gas or reducing gas. So this is the overall scenario of this modern nano-enabled or nanotechnology based sensor. What is the other point to be noticed? It is noticed that low temperature or room temperature sensor, some of the sensors available, it can work at say 300 degrees centigrade very well. Sensitivity is good. But still I have to warm this sensor to a particular temperature. So I have to spend some power to keep the temperature at say 300. But this is called room temperature sensor. So what do we start? That no background or residual effects. Second one is that room temperature phenomena. And the third one is the response time. Your sensor response time should be much faster, even 30 seconds, 50 seconds, 3 seconds, even sometimes milliseconds. So you will get this huge rise in current to its saturation value in a much smaller time. That means your sensor is very fast in response. So another one is the response time. So we found that no residual effects, sensitivity, that is what is the minimum amount of gas or liquid it can detect, LOD, limits of detection, in ppb level or ppm level. And secondly, we found that the response time is fast. But still, I'm not happy. Why I'm not happy? Because when in actual practical conditions, you will not find ammonia gas alone. Is it not true? That I am checking the soil constituents, then only nitrogen will be there. Potassium and sodium or phosphorus would be not there. It is of no use actually. This kind of absolute measurement does have no meaning. But the meaning is there, whether I will be selective in detecting a particular elements in the ambience or in the soil or in water. So my sensor would only detect ammonia in spite of presence of many other gases. For example, this is, say we have toluene, acetone, ammonia, formaldehyde, ethanol, methanol, and 2-propanol. These are all VOCs, volatile compound. But still we found their sensitivity with this kind of a sensor, graphene functionalized with biomolecules, only provides that sensitivity is much, much higher for ammonia only. And that is even at room temperature at 25 degrees centigrade. So you understand the evolvement or evaluation of a sensor, that from the conventional approach, where we require background correction, calibration, residual effect corrections, then selectivity is another huge problem, sensitivity, much higher. It should be, the limits of detection will be much low, and the sharpness or the response of the sensor. So all these things now we are adding more and more improved property into the sensing, okay, by using this nano level. So that is the electronics, where we are constantly trying to develop with the newer and newer modes of sensors. Okay. Hope you have understood this. Now, what kind of materials of choice? I said that the graphene we have used, and the graphene molecules will be dropped. Simple process. When you have this, first of all, let me talk about the graphene, which is basically, it is carbon at a different allotropy. And allotropy means it is sp3 hybridized and sp2 hybridized composites. sp2 is called graphitic characteristics. sp3 is diamond-like characteristics, tetrahedral kind of a bonding, and sp3 hybridizations, 120-degree angle of the bond. So we found that what kind of wave number, this is called the FTIR spectroscopy. This is the X-ray diffraction spectroscopy to find out what kind of graphene we have developed. And when you talk about the black one, is called the original graphene. And now when we called reduced graphene oxide after some processing, the red color is this. And it gives you a particular peak, okay, at a particular angle, and which deviates from, say, 10.48 degree for original graphene, and then graphene oxide, reduced graphene, introduces 24.5. There is a peak shift in the right side. Okay, so this is the effect, the XRD effects of that. That means definitely the when there is a XRD pattern or peaking changes, that means the order of the molecules or the atoms are also changing into the system. From the one network, which was primarily, say, sp2, now becoming sp3, like that. And we have two phases, both sp3 and sp2, and their ratios called IT versus IG. The both are not 50-50. We call it diamond phase is more dominating when the sp3 hybridization is dominating, and when this sp2 graphitic phase is dominating. And higher the temperature, the diamond phase to graphitic phase transition down. So depending upon what kind of sensors you want to detect, whether sp2 hybridizations will improve the performance, or it will be sp3 hybridization will give you better results. Entirely onto your requirements. You can play with the ratio of the graphitic and the diamond phases of the graphene. So this is graphene, which is functionalized with some biomolecules to give the selectivity into it. Selectivity means only in ammonia, when it is exposed, then I find the change in its transport and corresponding change in the current and voltage. And for other gases, it will not that effect. So screening effects, that is called the selective effects, is coming into this structure. So you have to check with the AFM to check the roughness and so on. So these are all the material characteristics. FTIR, X-ray diffraction, Raman, atomic force microscopy, field enhanced scanning electron microscopy, and field emission and high resolution tear. So we can find those graphitic palettes on the top of the surface of the interdisciplinary pattern. Now we look at the various sensing performance of RGO. One of the most important part is the stability. For any sensor, stability is very important. That is, how many cycles it should work. Suppose the sensor you have used one time and it is cannot be used in the second time, is of no use. The market will not respond to you. But look at here, even this is the first sensing. If you look at second, third, and onward, 10,000 cycles, 10,000s of sequence of sensing, we find there is no change in its response. That means it is highly stable. You can use it many times. So that's why that you can reduce the cost and product will be more attractive for your business. right? So this is the sensing for say ammonia. Now coming to the another pattern. When I talk about flexible on a plastic, then plastic means suppose wearable, or if your device is actually you can bend it. But if I bend it, then whether the sensitivity will change or response will change or not. So you can find that there is obviously some change with the bending, but not much. If you look at here, the percentage change is negligible. So bending of that substrate, flexible substrate, is not changing my sensitivity that much. So that is the objective of function. Okay. So another is the response time is not also changing, and the stability. So there are 5 things that are important. One is the sensitivity defined by LOD. There is a limits of detection. Second one is the selectivity. Among other gases in the ambience or liquids, how the sensor is responding to a particular species. So in this case, ammonia. Third one is the stability. How many cycles of operations the sensor would be working as same as the first one. Fourth one is the response time. So it should be fast so that I need not to wait for a long time to get the data. Before the parameter changes, I like to detect for online detection of something. And the fifth one is the flexibility and its reliability, and both are important, and the cost. So its worthiness of the sensor defined by all these parameters. Now coming to the next one, that you can tell, but ammonia I am detecting, but ammonia or in soil, water content, okay, and the moisture contents would differ. So my sensing will differ. Suppose at say RH value of 93% at say room temperature 25, I am trying to get the concentration of ammonia, and say I want to do the same thing at say 22% of relative humidity, or we find that the changes with the response time of different devices at different humidity is not very dominating. So you will find that there is a change, but it is not that the performance will be highly deviates from its value. So humidity, you have to make the sensors immune to humidity change. Then your sensor will survive, especially in this case of smart farming. Okay, humidity and water content. So it should be, it is very difficult to make it the hydrogen molecule, H2O, presence of H2O, the sensitivity will not change. So this is another attributes you should have, especially for sensor for digital farming. Now coming to another one, which is not a gas sensing but liquid. And this particular approach we are taking for the soil sensing, but I will give you an examples of how to detect the mercury presence in water. In that case, we are making, so this is my source and the drain, 2 electrodes, metal electrodes, and in between there is a gap which is not shown here. I have a better picture, I can show, yeah. So you can see this. This is the substrate, suppose silicon or glass. On the top, you have this metal pattern, very simple. And there is a gap you can see between 2 metal electrodes, extended electrodes. And on the top of that, you are dropcasting the sample. So the sample is dropcasted over there. Now we want to see the same IV characteristics. So I can have multiple such sensor on a substrate at one go. And I can detect the IV characteristics by dropping the functionalized materials like RGO sheet, we can reduce graphene oxides. And then we drop cast the water containing either mercury or lead or any other heavy metals, arsenic. Then we check that if you look at the various forms of this, then it depends upon the particle size. That means in the graphene, the particle size is another very important aspect for determining the sensitivity of that. So look at very carefully about the various facets of this at various magnifications. And we found that there are many fine features in this graphene nanosheet. And from this figure, at least one thing I can say, that my surface to volume ratio is much higher. So I have a huge surface to volume ratio. So nanotechnology will enrich the surface to volume ratios. What is the meaning for us? Because if the surface to volume ratio is high, then for a given constituents or species which I want to detect would have more coverage to the surface. And then it will introduce more changes into its physical property like current or voltage, so that I can be able to detect even the minutest amount of species broadcasted on it because of this high surface to volume ratio. So that is the advantage of going into nanotechnology, where the surface to volume ratio is high. Now coming to the various analysis, FTIR, XRD, characterize that one. Then we find that how the current and voltage changes with different parts per billion of some sensing like mercury. This you see that mercury. This is, you call it lead, you call it arsenic, and it is cadmium. So what is the difference in between the sensing? You find that changing in the current, if you look at changing in the current, is much more dominating in case of mercury. So detection of mercury would be much more easier in this case, because other contaminants like lead or arsenic does not have this kind of effects on its conductivity channel. But mercury has a very dominant. So drop in the current, that will, I can sense from the drop what is the amount of mercury has been broadcasted, and from there I can calculate the mercury concentration in the solution. So this way we are checking the current and voltage, which is also reduced graphene oxide based sensor for detection of mercury in presence of other metals like arsenic, cadmium, lead, and other heavy metals. So you can see there is a marked selectivity in this. You can see from there, the mercury has got a higher selectivity, where rest of this like lead, cadmium, arsenic, the selectivity is not high. So it gives you the almost like a normal characteristics, unchanged characteristics for, you cannot detect whether it is arsenic or it is lead, but you can detect whether it is mercury. Because we have selected the graphene and functionalized with certain way, so that only selectively mercury gets absorbed and we get the values. Now we compared with different kind of sensitivity, and this is your without mercury and after adding mercury, how much is the change in the current, and from there we are checking with this. So for example, the sensing material is zinc oxide, say nanorods or nanoballs, which is functionalized with bovine serum albumin. There is the most common protein, and that will provide you a sensitivity of 6 nanoampere per parts per billion. Of limits of detection is 0.36 ppb, and reference you have in the 16. You will find that this BSA we have used is a very simple protein obtained from the cattle. And deficiency of BSE protein means there is some problem with the cattle. Okay, so I think those people doing veterinary science, you know it much better than us. Then in case of DNA functionalized CNT, there is a DNA around the CNT and then forming that as a network or changing the current, then we found that sensitivity is 10 nanoampere parts per billion change in the constituency of mercury or the lead or something. Then metallothionein functionalized RGO. So we functionalized with metallothionein, and we find the change is much higher, 200 nanoampere per ppm. And when RGO, reduced graphene oxide, will decorated with gold nanoparticles are used and triglyceride acid TGA, then we are getting much higher response, 300 nanoampere per ppm. So if you look at the gold nanoparticle, the structure you can find that you will find that the nanoparticles are dispersed over the graphene flakes. And this graphene flakes, you can see how this nanoparticle dispersion over the graphene flakes improves the sensitivity in these fashions. And we have tabulated that one to give you an idea that more the current at the same condition, I will have more benefit as a sensors. Now coming to the, with this concepts, let us go to a very interesting applications which I have actually discussed in my last interaction with Nahem about a variable rate fertilizer applicators. At that time, I promised that I will do something so that in spite of getting soil mapping, prior soil mapping, the fertilizer pattern, how can I make a closed loop control in the smart farming? So what is the idea? It's called precision farming. So what is the requirement of the fertilizer? To compensate the particular constituents or the nutrients of the soil, I will that introduce very precisely. So to ensure it, we have to know first what is the constituents of that. Then we will make that dispersion. But we will show you first how we can make, if that information is available to us, how we can make an applicator so that precision amount of fertilizer can go to the soil. So this is actually, we will show you how this can be done. So I am just coming. I will go to this part, the difference of sensor means how the difference of the, when prior data, how we can plan to dispense the fertilizer in the soil. And then finally, I will show that even without prior data, how can you make smart farm? So the sensor will be itself in the loop. So sensor will detect online or in situ what is the constituents of the soil. And accordingly, my dispensing circuit will be actuated and the correct amount of fertilizer will be dispersed or dispensed on in the soil. So that is called precision and smart farming. So we have done the, first of all, the is a huge acres of land, right? So when you have huge acres of land, then first of all, you have to locate the land in very precise manner. So you have to actually, what I say that I am going quickly to the, suppose in the soil. So you have actually this is my land, okay. So I have made several grids, and this grid is this is a coordinate. So what is it? And this is my y-axis and x-axis. These are all made by you. Then you have put, this is my 00. When I say 00, you can find this is the grid. And the grid may be say 10 meter by 10 meter. It is 0, 1. So this one, 1, 1 is this one. Like that, you can make hundreds of such grids. Right? A 1 acre of land. And definitely the grid size and width should be more than the footprint of your tractor. And the tractor, while actually is placed, say here in this place, then you know that what should be the corresponding coordinate of this. So to get that information, what we do, there is a GPS connections through satellite. From the GPS, this satellite, from the GPS, we know the exact location of that. Okay, and prior to put the tractor, we take samples, say any arbitrarily, this grid, 5 spots, 1, 2, 3, 4, 5. 5 places we detect the constituent, say, nitrogen. Okay, suppose I am doing urea. So how much urea is required to be dispensed with, or how much, whether at all we require any or not. Definitely I am not interested about the topsoil. So I will go actually 6 inch or 8 inch below, take the sample offline, and then I measure what is the nitrogen, available nitrogen content, not the total nitrogen content, which will be for my micronutrients of the soil required for a particular crop grow. So we know very precise, and we will map that into this GPS coordinate system, so that when you tractor will go to that point, satellite link will show there at that grid, and this is the composition of the micronutrients in this grid. Accordingly, my tractor would have the hopper, and by rack and pinion, we can actually push the fertilizer as the requirement. So I will go into the details of that. So that is the objective of a particular applicators, a smart applicators based on the satellite and GPS connectivity. So it looks pretty exotic for you. But if I can develop in situ measurements, my tractor would have a sensor with the robotic hands. So it will dig into the earth, take the sample, measure it in the site, and give you the data. And feedback, it will go to your controller circuits, which will dispense the fertilizer as per the requirements. So that is the main purpose of my research, okay, of my team, how to do that. So let me go back to this. So what I say that, first part, you should know that everything should have a starting and ending, right? So when you look at this, I am just explaining you today's approach to the smart farm. We have a tractor, and we have a GPS directional transmitters. We have a funny laptop, okay, funky, and yeah, it's pretty sophisticated. And you have a DGPS base station. You transmit from there to there. From the tractor, it will go to the base stations, and from the base station to the satellite, and from the satellite again to the base station, and then you go like that. So the whole digital mapping of that is available in the cloud. Accordingly, you are dispensing the fertilizers. Okay? But you need the prior sensing of the soil constituents in this technique. But without going into that, how to do that? First, we try to say that how we can reduce, because this will cost you more than 1 lakh. And our target is to no way the price of that additional component required for smart farming would be at least 10% of the total tractor cost. So if say, for example, if it costs you say 15 lakhs or 10 lakhs a tractor or 5 lakhs a tractor, then our target is less than 50,000. But finally, I will show you how it can be done only by 5,000. That is the final thing. That means 1%. So I can really add value to my tractor. So tractor will be buying only 1% of the cost. Okay, he can transfer the whole mode of his technology, okay, to a new domain without much cost. This cost much higher than the additional cost of electronics. That is the objective of this work. So we don't need a DGPS rover. We don't need a laptop. We don't need a base station. So cost straightway reduced. What is the approach? That it will cost you DGPS and laptop. So 4.5 plus 30, 4.8. So 4,80,000. But what we'll go for, we'll need an LCD touch screen, which is 2,000 rupees. And UV locks GPS module. Now GPS modules are not so expensive. It is 2,000 rupees. And Raspberry Pi Arduino board, which will cost you 3,000. The Raspberry cost you P1 to 3,000. So 2 plus 2, 4. 4 plus 3, 7. And this is 1.5. So 8.5 thousand. So 8,500 rupees, you can have the same function which you are investing 4.8 lakhs. So that is around, say, huge price. When comparatively, it is the same price with the tractor. So market will not take you. Okay, until and unless you are pretty rich. So I cannot sell it in India. And that I've already explained you that we made the grid and IIT. This work carried out in collaboration with Food and Agriculture and Food Engineering of the IIT Kharagpur, one of the biggest agricultural institutes, departments in India, and electronics department. So we have made this kind of survey and then put it in the lookup table like this. That grid number 1, what is the amount of nitrogen, and correspondingly what is the amount of urea. So we see that this is 8.6 nitrogen kg, that is kg per hectare. Then the urea is 19, but my requirement is 400 kg per hectare. So I need to add 381 kg of this per hectare, definitely per hectare fertilizer, urea over there. Am I clear? So this is my detected nitrogen. From there we know what is the urea content on it and what it is the requirement. And from the difference of that, for that grid 1, this is the difference of that I have to add per hectare. Like that, we have made hundreds of grids in acres of land, and we have the prior data, this data. What is the actual constituents of that? Then we have made, this is the requirement. So these are all programmed in the microcontroller. Okay. Then when the tractor will be at that positions, then accordingly the hopper will dispense the fertilizer based on that requirement, which is in the rightmost levels to give an ideal constituents or nutrients of that. So these are red, what is existing, and then the blue one, which is being added. Ultimately, every land piece or the whole land area having got the same nitrogen or urea content. So I can say that by very precisely I have fertilized. So this is GPS enabled one, and this is the visual display and all these things. It is These are gimmicks. So this you can learn in 1 week. So not much things. So taking about the concepts, okay, that is more important. So these are the GUI interface. So you are all students now very much interested about that. So it is very friendly. On the digital LCD film, you have to put that one and get that value. And we want to make it so simple that it will be automated in nature, so that the farmer will not require to learn the nitty-gritty of the electronics. So this is what I try to say that. So this is the rack and this is the hopper. We put the fertilizer, then there is a slit, okay, and there is a linear motor at the end. So depending, this is the motor at the end. Rack and pinion, this is a linear translation of this hopper, the slit, and slit opening and duration of the opening, depending upon how much fertilizer you require. If you require less number of fertilizer, for this case, maybe the slot will remain open for a smaller time, okay, but for the higher requirement here, the slot will be open for a longer period. So we have programmed it in that way. The aperture clearance, original time it is closed, no fertilizer is dropping. When the tractor goes to a particular section of the grid, then from the GPS locators we find out, so this is the soil constituents. Accordingly, my linear motor will translate and stop with a particular size, aperture and duration. It will dropcast that one. We have checked on a plastic bag exactly whether the additional requirement is being placed or not. And we are getting a data set out of it, and statistically you have to find out what will be the optimal speed of the tractor for which we'll get the best performance and so on. So you can make a lot of stories. So I'm not going into the story because this part I told you earlier. But that time I promised that I will do something which will not require the GPS, even much more smaller way. So my next part, I will concentrate on that very quickly because time is almost over. But I have given you the glimpses of what I am planning to do and what I have been able to do. So this is all hopper and all this, you are better. I am getting out of that block. Now coming into this, these are Arduino boards, and these are simply you can download from the website. So not a big thing. And GPS standard literature, you can find out how to interpret the data stream of a GPS. That is the azimuthal axis and all these things. So okay, fine. So I'm not going into that. I have explained in details in my last lecture. So coming into the next part. Yeah, next part. Whether we can make some kind of a NPK sensors, okay, which will be real-time. Real-time NPK sensor, and where I am coordinating or collaborating with Parvani. They are providing me the soil. Today I will show you some results. And my team member is my director of this institute, Professor Day-3, myself, and some of my faculty members which they have interacted in their last visit, Professor S.K. Das Mandal, then Pranav Ganguly, and my technical staffs, S.K. and research scholar, and Mr. P.K. Dev. So let me just give you, what is the idea? That there will be a DC motor. I am not going into the details of that because I have not yet patented that. Okay, and this is the sensor part, optical sensor, which will be around the cylinder. Okay, and the cylinder would have a robotic hand, and this part of the cylinder would have the tapered head so that it can dig into the soil. And there are rotating conveyors which will convey my soil to the top. And we made it by controllers such a way a particular amount of soil will go and then it will be mixed with DI water. All are controlled internal. So I am getting a soil solutions in water. And then we actually made some kind of a laser source of different wavelength to check the constituents of the NPK, okay, depending upon this wavelength of absorption. So this is the robotic arm will just go inside. The tractor will be there in that grid, and you will insert inside, say 8-inch, 12-inch, 6-inch. You'll go as per your requirement and collect the soil, and in there they will start measurements. So in this region, it is a measurement chamber, and this is the soil conveyor, and on the top the scores. And here the data is coming. Then all the data acquisition and the processing will be embedded into the system. Finally, at the end of the day, I want to see what is the constituents of the nitrogen available, phosphorus and potassium. As per that, it will feed back to that circuit, which I have shown that if I know NPK, then accordingly I will dispense, say for example, in urea for nitrogen deficiency. So this is the whole objective of this. So no GPS, nothing, only this kind of a smart online or real-time. So this is the whole lab setup what we have developed. That there is a spectrum analyzer. This is called benchmark. We take the samples from Parvati and from our side and look at the absorption spectrum and calibrate with the chemically found data. And then we found that from the optical spectrum, we make the white light, illuminated that with the lens. Then by various gratings, lenses, we make the wavelengths for 400 nanometer to 1700 nanometers. So these are all set up. And the soil cuvette we have made, and the soil sample will be there in the cuvette. So we found that there are a particular kind of spectrum for nitrogen. We found there are 3 such absorption wavelength. One is 450 to 550, other one is 438 to 490, and other one is 470 nanometer. So it is up to you which peak you will choose to detect the constituents of the nitrogen. For example, in phosphorus, we have 800 absorption peak is 800 to 970 nanometer, then 528 to 529 nanometer, and 950. So this is in the infrared zone, right? And this is in the visible zone. 400 above is the visible. So this is 620, so almost in the visible range. So for the potassium. So we have isolated, segmented the spectral response of the soil by exposing the soil into white light and other side absorption spectra. Find that what is the wavelength for a particular elements. And from there we try to quantify some kind of a machine learning with the chemical data. And the oil, water constituencies vary to find out the expert system. So for a 5 gram soil, we are introducing 20 ml of water, 22 ml of water, 24 ml of water, 26 ml of waters, and find out what is the nature of the absorption. Then we find that, for example, for phosphorus detection, these are the various, say 20 milliliter of water. Then 5 gram, all the constituents of the soil is 5 gram. But I am changing the water change and see the absorption peak. One thing I am rest assured that my absorption peak doesn't change with the water content in it, but it changes the peak value with the water content. So that is one thing is very clear, that if you want to make absolute value of its value of phosphorus or say nitrogen or potassium, it is totally depending upon the water contents in the moisture. So that is a very important parameters. Here lies the machine learning approach for that. So there will be a soil moisture sensor to find out the constituents of the moisture, and we have to put it in that data matrix so that we can find out the value of the constituents amount of nitrogen, phosphorus, or potassium. So this is for potassium. We found that is the band, and different oil or water. This is this. And then if you look at the whole approach for that, so this is the fitted things that will be inside that on the tractor with that rotating part. Then there is a transimpedance amplifier because current gets amplified, then it will be converted, data acquisition. Then this is the machine learning, the feature extraction, estimation, and result display. So that is online, you can have the display. Plus, we can take the raw data to my feedback loop so that my tractor would have a current amount of feed voltage. So the linear motor will accordingly will translate into the movement of the slit and the deviations. So that accordingly we will get the fertilizer dropping in on that particular grid as per the requirements. And if we require after the data acquisition, you can make a plot. So you can send it to the cloud when all the GPS information. So you can make a total map of the soil very fast just by this kind of a automated online measurement setup. So that is the whole thing. Now, parallelly, I'm trying to develop the concepts which I gave you in the first slides. Whether I can use the nanotechnology in spite of the optical sensing, whether I can give a fate-based sensing that is called smart and active sensing. So this is another group of my students working on it. It will be a simple effect transistors. So this is the silicon dioxide, then this is the aluminum, and then hafnium dioxide is the dielectric layer. We have deposited that one by one. And this is the source and the drain, and this is the back gate. And here we'll have the functionalized RGO. And we find very good response for mercury and lead and arsenic. We are expecting we'll get even better response for the ionic contents like sodium and potassium and also nitrogen. So that is, we will do the same thing, the same data acquisition and the machine language platform. Only the sensor head will change. The sensor head here is the optical one. It will be replaced with the active fate sensing. Entirely new concepts. So once we do it, my cost will be much lower. So fate sensing, it will be much lower cost. I can put it on a plastic display. Fate sensing can be done on a plastic. So this is my dream for the next 1 year. Okay. The first one has been started to show me results. Okay. And it is very much, data is very much close to the data of what Parmani has sent me. And I am seeing the difference, but I'm not yet satisfied. Keep on interacting with my students and all, so that I know that data is finally is really, I can say, yes, it is working. So still that war things take times. So, but I'm showing, it's my very, I am getting thrilled to show you these results. So this is the 2D model which we make that first, any device we have to make the model. And my sensor, you can see that how many sensors, this kind of sensors can be built, 20, 25 in a 2-inch wafer. And we will do that but it costs 50 crores for this. So don't worry about doing it in a small lab. I have a huge lab what others have seen where I'm developing these systems, fabrication of the device. So we are fabricating the devices and trying with various kind of samples. As I shown you, ammonia detection as well as the mercury detections. I am successful. Now I am going into nitrogen, phosphorus, and potassium. So probably I have just 10 minutes more. So I have been able, this is the noise reduction. So when the signals comes, then you need little bit of little bit of feature extraction means we have to get rid of the noise. So those things are being done by signal processing. Look the original signal and how the noise are fine. It's very good final results we have come. From there we will make our expert systems. And this is the feature vectors and all this, depending upon the empirical mode decompositions and all we are using for noise reduction. And there are many works. I like to use LED in spite of laser, so the cost will be less, and I can make this product in much less than 10,000. So with this, I like to end, and thank you very much for your kind attentions and your patience to hearing that. So this is the latest one coming from my lab. So I am also very happy to share it. If you have any questions, you can ask. Thank you very much.
Was very in-depth lecture for us. Any question from students?
I would like to thank you very much for Bhattacharya sir, IIT Kharagpur.
I can't hear you. I just can't hear you. So if you are a little louder, I can hear you.
Thank you very much.
Oh, okay, thank you. Yeah.
IIT Kharagpur for giving its detailed description about the sensors for smart farming. The team VNMKB and the audience, the Nayak Center VNMKB Parvani is thankful for your such a wonderful lecture. Thank you very much, sir.
Okay. Thank you.
On behalf of NAHEP Center, I, Dr. Gopal Shinde, Principal Investigator, very much thankful to Dr. Bhattacharya sir for being with us and such a huge exhaustive work which is you have explained. But more than that, we have experienced with you in person in your laboratory.
Yeah.
And your all types of those things which you are running through with the students. It is really amazing and it is very much impressed to all of us. And most of the faculty now they are asking me to visit the IIT campus. Also, some of the students they are asking me to visit the organize the visit to IIT campus. And I'm eagerly waiting for the training program to be conducted by IIT Kharagpur campus. I request you, sir, please convey the same message to Honorable Director, sir, and Professor Machan, so that we will be accompanying there. Our presence in your campus will be blessed to us, and also your presence in our campus will be blessing to all other students and campus people. And thank you very much, sir. Thank you for being with us.
Thank you very much. Bye-bye.
There is one announcement. After the lunch, we will gather at the same place at right at 2 p.m. Thank you, one and all.
There will be a lecture. There will be a lecture on